How y'all doing?
All right.
Any questions about anything at all before we get started today? All right. Well, we've been working on chapter 4 for the last week or so, week and a day. And my goal today is to try to tie all that together into one additional big example before moving on to the next thing on Friday. So, let's quickly review everything we've done within chapter 4 so that we may apply it together here today. First, the laws of motion. In brief, they are 1, the law of inertia, stating that matter is lazy and it's going to do whatever it's already doing until a force changes it. Law 2, net force equals ma, and law 3, action-reaction. We have also talked about various different types of force, highlights including gravity, which is a synonym to weight, gravitational force, which is the same as weight, normal force, which is what happens when you push into a surface and it pushes back out as a counter, which is the reason you don't fall through the floor. Tension, which is the force exerted by a string. Notably, strings always pull inward with the same tension on both ends of themselves as a counter to being pulled outward on both ends. And friction, which happens whenever matter tries to move through or across other matter, and it is a force that opposes motion. We're going to tie all those together today in one big example that looks something like this. We have two objects tied together by a rope. The rope is going to add tension. One of those objects is sitting on a surface, so that's going to create friction. They both have weight because we're assuming this happens on planet Earth, and one of those objects is sitting on a table. So once again, that's also going to generate normal force. So everything we've been doing all week tied together into this, and we're going to do it together. So, once again, to look at the basic scenario here, we are going to build a pulley system where two different masses, one of them weighs 100 newtons, the other weighs 50 newtons. That is, again, weight, not mass. They're going to be connected by a string. That string is going to run over a pulley, and the objects will be arranged thusly, with object 2 hanging over the pulley and object 1 sitting on the table. Now, if I was to build this and let it go to start doing whatever it is it's going to be doing, what are some of the things you could expect to happen if you were watching this on a table? I just built that and let it go. What sorts of things could naturally happen if I do not interfere?
What could happen is box 2 goes down while box 1 slides to the right on the table towards the pulley.
All right, very good. Correct. If the table is not very frictional, would be one way of saying it. If the table does not generate that much friction, it is entirely likely that object 2 will be pulled down, and in doing so, it is going to pull box 1 forwards along with it. They are tied together. If one of them moves, the other's going to have to go with it. Now, let's say that the table actually does generate a lot of friction. What instead might happen?
Nothing, that just stays still.
Nothing. Friction likes it when nothing happens, so if friction is particularly strong on this particular table, like say it's very rough, then it's possible friction will be enough to just lock box 1 in place, in which case nothing will move. Those are the two primary realities here. And what type of friction will act in either scenario?
Static.
Which version would static take over in?
The stationary.
All right, if everything remains stationary, the table will exert static friction on box 1, very good. And if things begin sliding, what type of friction will exist instead?
Kinetic.
Very good. So the type of friction that exists is going to depend on what happens. And we are going to treat this whole situation as if it's going to start sliding. That's the more interesting example to look at. So we're going to assume that this friction will not be strong enough to hold everything in place. So nothing is going to begin, everything is going to start moving. The boxes are going to start, box 1 will slide, box 1 will descend together at once. Wait, I said that backwards. Box 1 will slide, box 2 will descend. And in that case, kinetic friction will be the type that acts. We've been given 2 different mu's, one for mu static, one for mu kinetic. And if we're assuming that things start moving, we're not going to need the static one at all. It is here as a red herring. So if things are moving, kinetic friction is acting. This is the mu we're going to eventually use, not this one. Some questions might give you the type you don't need as a red herring. So pay attention to how they're labeled. And pay attention to what type of friction would act in a given scenario. So this system is going to start moving. And we need to figure out, as a result of that, how fast are all the parts of this system going to accelerate, and what will the tension in the string be? So it's the main 2 things that we're looking for here. Any questions thus far? So I've just gone ahead and listed the things we've been told. That would be the weight of the 2 boxes, 2 coefficients of friction. We want T, we want tension, we want acceleration. We got to figure out how to find them. Before we start doing any math, I want to make a few observations about this scenario with you guys. Observations that we can use to make a few assumptions that are going to help us. Observation number 1. In both scenarios I described, one where nothing moves because static friction is too strong, and one where things do start moving and kinetic friction starts acting, both of these boxes start moving together, right? It's all or nothing. Either they both stay still or they both begin moving, correct? That should tell us something about the acceleration of both boxes together, because we're going to work the version where things do start moving and box 2 is going to descend and box 1 is going to get pulled forwards. They are physically tied to each other. So if box 2 takes the, I've been calling them 1 and 2, so let's label them 1 and 2. If box 2 takes the lead and starts descending, the rope is going to pull box 1 forwards along with it at the same rate. They're tied together. They have to proceed together at the same rate. If you and a bunch of people are sitting in the same car and the car starts accelerating, you're going to accelerate at the same rate because you're all physically attached via your seatbelts. So whatever either object's acceleration is separately, they should be the same number. They are tied to each other, they are stuck to each other, they have to accelerate at the same rate. Which means we don't actually have to look for 2 different accelerations, we're just looking for 1 acceleration. Because if you find one, you find the other. There's only one small problem with that, and it's that the function of a pulley is to change the axis that tension is pulling in. I'm going to elaborate a little bit more on pulleys in just a second. For this argument right now, for the acceleration argument, I'm going to point out what direction is box 1 going to start accelerating in?
Positive X.
Positive X. What direction is box 2 going to start accelerating in?
Negative Y.
Negative Y. Those are 2 different axes, and more importantly, one of them is normally positive and one of them is normally negative. So even if we work this through and these two numbers have the same magnitude, and we treat them like one number, the vector directions state one of them would be positive that number in the x-axis, and the other would be negative that number in the y-axis. So we are going to treat the accelerations as the same, but when we look at the two objects separately, we're going to have to take that into account and make this negative before we do anything with it. We have to add an extra negative sign or our math is going to not work right. We have to take that into account because of the direction everything's pointing in. Is that an okay assumption? It's still better to treat it this way than to have two separate A's, because then that's an extra unknown we have to find, and that's a big old headache. We've got one unknown, it's positive in one place and negative in another. Now, the other observation that I want to point out, not only do these two things share the same acceleration, they're going to share the same tension because they are tied physically to the same rope. And by definition of tension, ropes pull with the same force inward on both sides. And that is irrelevant of whether there is a pulley attached. The purpose of a pulley is only to change the axis that a rope is existing in. But the rule about tension pulling inwards on both sides remains intact. It's just what direction each side points is changed by the pulley, but it's still inward. To kind of give an example of this, here is a poorly drawn old-timey pulley, say like at a dock or a ship or even like behind stage at a play or something in a theater. It's got a rope run over it. On one end, you have a person pulling down with, just as a sample number, 100 newtons of force. And on the other side, they are lifting up a box that weighs 50 newtons. So those are two different forces acting on the two different ends of the rope. And what the pulley has done is, normally it would be, if we were looking at a flat level rope like in tug of war, the outward forces would point left followed by right, and the inward forces would point right followed by left. Again, what the pulley does is it just bends the string and changes the direction of each of those. So here, the two outward forces both point down. And this, I hope, is consistent with how you've noticed ropes and pulleys like this before. You tend to pull down on something, the other end tends to rise, but its own weight would still be pulling down. Now it rises because on that end, tension will point into the rope, which from the box perspective is up. Meanwhile, as you pull down on this end, it is also going to offer resistance upward. It's still into the rope, what that means is just adjusted by the pulley. So it's still inward, and it is still the same number on both sides. Whatever tension the rope pulls upward on the box, it's gonna resist you with the same amount of force as you pull on the other side. So, again, probably said this a million times, the main function of the pulley is just to change the direction that these are happening in, but it's still inward regardless. There is one other observation I want to point out though, and it's that it's the same tension on both sides. So over here, I've gone ahead and written in just the same T twice for that reason. And thankfully, they're both going to point in positive directions, so we don't have to do the same thing with the A's that we do over here. They're both going to be positives, so that's nice. The weird thing I want to point out, the tensions will always be the same as each other, but that does not necessarily make them the same as either of the outward forces acting on either end. The tensions will be the same as each other, but that does not make them the same as either one. Note that in order for you to be lifting the box, the outward pointing forces would have to be in balance, right? You would have to be supplying more force into the rope than the box weighs in order to lift it. So the forces need to be in balance for the box to rise. But not only are the outward forces not equal to each other, they are not equal to the tension either. The tension would in fact need to be somewhere in the middle in order to create the desired effect here. It probably wouldn't be literally 75. I'm just giving that as the halfway point to make an example. From the box's perspective, gravity's pulling it down with 50. The rope would need to exert more tension upwards than its weight to actually get the box up, right? So the tension would need to be bigger than the weight of the box. But on the other side, you don't want the rope to be lifting you upwards, right? So the force you pull down with would need to be bigger than the shared tension on both sides. So bigger on one side, resulting in net motion up. Smaller on the other, resulting in net motion down. Again, just the two different sides across the pulley. So, and we're going to demonstrate this here as well. The tension number is the same on both sides, but it can still be different to the force acting outward on both sides. And that has to be the case for net motion to occur. If all these forces were even, nothing would move. So there has to be an imbalance somewhere. But regardless of the imbalance, the tension numbers will be the same. We're going to prove that here today. Any questions or issues with any of these assumptions or how they relate to situations you may or may not have seen before? Okay. So, because of all this, despite there being two different objects, we are only after one united tension number and one united acceleration number. There are two unknowns we're after here. And that means just to give the game away, we're going to end up in a two equations, two unknowns scenario. So this is also practice for that. So, the goal is after acceleration and tension. Given that there are two different objects with various different forces acting upon them, I'm going to recommend we begin by looking back at this image and figure out all the forces that are present by drawing free body diagrams and just physically listing all of them out as arrows. And then we're going to do vector addition, figure out how they all add together to cause the net acceleration of this system. I'm going to start with box 2, actually, just because it has fewer arrows. What forces are present on box 2 in this situation?
Gravity and tension.
Very good. It is that simple. It's not on a table or anything, so there's no normal force, and it's not touching anything, so there's no friction to speak of. There's just its weight down and tension up. Those are the only two.
Shouldn't that be FG2?
It should, thank you, sorry. Please call me out on my mistakes. I am human and I make them. So, box 1 is on a table and the axis is shifted slightly. So, what forces would be present on it?
Friction, tension,
Friction and tension, very good.
normal force, and gravity.
All right. And I heard multiple people answering things, thank you all. Now, friction would be present. What direction is it going to point if things start moving as you expect them to? Very good.
Negative x-axis.
Yep. What direction is the motion going to be? Positive x. By definition of friction, it always opposes motion. I'm going to draw it down here because I like to visually represent that the table is doing this. So I'm drawing it parallel to the table, like along the line of the table. It is just an x-axis force. I just put it there to illustrate where it comes from. And again, friction opposes motion. If box 1 begins accelerating to the right, friction is going to pull to the left to try to stop it. That is always the rule. Figure out the direction of motion, or even attempted motion, friction points opposite. That is every force acting on box 1. So, 2 boxes, several different forces between them. We need to see how they all interact together to create the net acceleration that we are observing within this system. And to do that, we need to do net force equals mass times acceleration for both objects and every axis that becomes relevant as we do that. Box 2 has fewer things, so I'm actually going to start here again. We got 2 forces that are contributing to the net force acting on the box. So sigma F for 2 for the net force acting upon box 2. Definition of net force is just all the forces present added together. There's only 2 of them, and conveniently they both point in the same axis, so we can't just add them up normally. This is basically a y-axis operation. I will label it as such. Tension up, force of gravity down. We'll just add it in as a negative number later. And by definition of net force, what, bless you, should those 2 things add up to? They'd add up to 0 if the system was not accelerating, if everything was locked in place. Instead, things are going to begin moving. We're examining the scenario where I let go and things do slide, like this. In that case, what instead of 0 should they add up to? We don't have a number yet, but just tell me the formula for it.
Would it just be mass times acceleration?
It would. It would be, and that is again from Newton's second law, net force equals ma. That would be the mass of box 2 times the acceleration of box 2. Now, I've already determined that the 2 objects have the same magnitude of acceleration. We'll take that into account later. I'm just going to write A2 now for completeness sake. And within this formula, we're, bless you, showing how these 2 things work together to cause the resulting motion of the box. Now, if these 2 forces were equal, but opposite, they would add up to 0 and A would be 0. But that's not the case. That tells us that the tension and the gravity, the weight of box 2, are imbalanced in this scenario. If they were balanced, everything would stay still. But if they're imbalanced, something's going to start moving. And this is a good place to start, because we want tension, we want acceleration, they're both here. We already have the weight of box 2, because it told us the weight is 50 newtons. That's not its mass, that's its weight. So we already have a number to put there. We do need to figure out its mass, but that'll be something straightforward we can do later. Right now, this is a good start. It's got the 2 things we want in it, but sadly, it by itself can't tell us anything more at this time. So we have to continue analyzing the forces on the other box to get another equation with our same 2 unknowns in it. But any questions arriving at this point on what all the pieces mean? All right, we're gonna do the same thing to box number 1, but the forces on box 1 do not all point in the same axis, so we have to do it once for x and once for y. If we wanted to, we could write out box 2's x forces, but there aren't any. So that's just gonna, if you want to write it out, you can, but there's nothing. They just go away. Now for box 1, so I'm going to write out net force box 1 x. So we're just looking at the x-axis ones for right now. It kind of looks like fix, so I'm being specific in that being a number 1. Box 1's x-axis forces are T forward and friction backward. And what are they going to add up to from box 1's perspective?
Should be a positive number.
There'll be a positive number because the box is going to accelerate forwards. And the net force will once again add up to this object's mass times its resulting acceleration. Different mass from before, but we know, because of our earlier assumption, that those two A's will be the same number. So we'll plug in a shared united A for that later. And now we have a second formula with the same two unknowns in it. T and separately acceleration. And so we're almost at the point where we can do our 2 equations, 2 unknowns trick. The only problem is, technically there's still more unknowns than that, because we don't have a number for force of friction yet, and we also have to figure out each box's mass. So there's a little more work to do before we can actually start finding A or T on their own. How do we find force of friction acting on box of 1?
Normal force times mu.
Very good. I got that formula here. Force of friction equals normal force times mu. And specifically, since everything is moving, we've already determined that we want kinetic friction. So we're going to use the kinetic mu. But we do have to quickly make an assumption about what is the normal force acting on box 1. Now, you may be able to jump straight to a number for that. Kudos in that case. But I am just going to show the math for where that number does come from, just so that you have all the steps written down. To do that, since normal force is acting on box 1 in the y-axis, I'm also going to do a net force analysis for box 1 in the y-axis. So F1y instead of x. Box 1's y-axis forces are normal force up and its own weight down. They're the only two. And what do those add up to? 0, because the box is accelerating in the x-axis and not in the y. So whatever its mass is, its acceleration is 0 in the y. So both of them just add up to 0. And once again, as long as something is just moving back and forth on a flat surface, you're usually pretty safe to assume that normal force and gravity will be equal and opposite. Our math supports that conclusion in this case. If box 1 weighs 100 newtons down, normal force in this case should also be 100 newtons up. Again, you are allowed to jump straight to that conclusion, but I like showing where it comes from. Now with that assumption made, or rather that number solved for, we can find a number for the force of kinetic friction. I'm keeping in all the absolute value brackets for a reason that will become apparent later. And so the absolute value of our force of kinetic friction should be 100 times 0.32, which is 32 newtons. Questions or issues arriving there?
Excuse me.
Now, I kept the absolute value bracket in because I do recommend them being here in this formula in the first place, because again, this is a cross-axis formula, and one axis doesn't usually know or care about positive or negative in the other. And that does technically mean our answer here is absolute value of 32, meaning it could be plus or minus 32. Given how we drew our picture in our normal reference frame for positive or negative x, which of those two options would we want to use when we plug it into this formula?
Positive. What, negative?
Negative. If we assume right is positive x, and you are allowed to assume something else, but for consistency's sake, I'm going to try to stick to mathematical norms. If right is positive x, left would be negative x. Our force of friction points to the left to oppose motion to the right. And as a result, if we keep t positive, our friction value would need to be negative to oppose it. So I'm going to plug in negative 32 for friction. Again, just to oppose the direction of tension. You could decide that left is positive, in which case you would need to switch these two signs. So that's force of friction kinetic taken care of. So we're just going to keep trying to fill in numbers in our formula here to get us to a point where A and T are the only two unknowns remaining. Next up is mass 1 and acceleration 1. We've already determined that these two objects share an acceleration, and box 1 is specifically accelerating in the positive x. So instead of A1, I'm just going to write positive A. Lastly, we need something for mass 1, because this is an odd scenario where we know the weight of the box, and now we need its mass, because once again, those are not the same thing. Written on the board is 100 newtons. Newtons is the unit for force, therefore that is the weight of the box. How can we use that to help us find the mass of the box?
Use the force. Normal force.
Divided by gravity.
Yes. Oh, yeah, I erased that earlier, didn't I? The formula for weight can be used backwards to find mass from weight, because G is always going to be negative 9.8 as long as you're on planet Earth. So in this case, we'd have negative 100 equals m1 times negative 9.8. Whatever its mass is, it's enough to multiply by this value to create a weight of 100. So thanks to algebra, we can pretty much use any formula in reverse. So that would be m1 equals negative 100 over negative 9.8. Those negatives will cancel, which is good because negative mass doesn't really make any sense. It implies either you're losing mass or you have anti-mass, which would explode. So let's try it. It's good that it cancels. And if my memory serves, that should spit out about 10.2 kilograms. Does anyone disagree? All right. So that's what we will plug in for M1. That is box 1's x-axis figured out, except for the two things we're after, tension and acceleration. So now that that officially has our only two unknowns in it, let's also fill in all the details on our other equation with the same two unknowns. So looking at box 2's y-axis, tension points up, its own weight pulls down. Make sure to track the signs on that. That's equal to box 2's mass, which we'll find momentarily, times box 2's acceleration. We described earlier that the two A's will be the same magnitude, but one of them points in a traditionally negative direction. So instead of A2, I'm going to write the shared unified A that's in the other equation, but it points down in this formula, and we have to add that negative ourselves, or the math doesn't work. It'll give us a weird answer that doesn't make any sense. Again, this is why you always have to make sure to keep very careful track of what direction everything points in. We like vectors, or rather, physics likes vectors. You're allowed to not like them. Now, we do need mass for box 2, and really the same method will work. It's got half the weight, so it should have half the mass, right? Just to prove that very quickly. M2 would be negative 50 over negative 9.8, which should come out to about 5.1. Does anyone disagree? All right. And with that, we are now at our beloved 2 equations, 2 unknowns scenario. And once you're at this point, you're pretty free to proceed in any method you prefer. Solving one, like you could solve the first one for A, plug it into the other for T. You could solve one of them for T to plug into the other for A. Either tactic works. At this point, you're pretty free to do whichever version you prefer. When I look at this, there's a slightly different path that I think to take, and it may not even be simpler necessarily. I just want to demonstrate to you that it works as an option. So again, there's more than one way to proceed from here. But when I look at these two things, I see that they both have A multiplied into something, but their T's are just kind of sitting freely by themselves. There's nothing to like multiply or divide or distribute out. I'm going to take advantage of this fact to, again, demonstrate a third option. I'm going to take these two things and solve them both for T. For the top equation, for box 2's y-axis, to do that, I'm going to take this 50 from the left and send it over to the right. So that's going to look like T equals negative 5.1a plus 50. And then for the other equation, box 1's x-axis, take 32, send it over to the right, and that'll look like T equals 10.2a plus 32. And now, rather than just solving one of them for something to plug into the other, I've now arranged both of them in the form of T equals blank. So that means I've now got 2 statements that both equal T. And according to various math properties, if 2 separate things equal the same thing, then they must equal each other, right? So to write that out, negative 5.1a plus 50 equals T, and separately, T also equals 10.2a plus 32. If all these things are the same, then you can choose to just cut out that middle part and eliminate T as a factor. So again, just a different way to illustrate the process of the 2 equations, 2 unknowns thing. You don't necessarily have to plug one into the other if you can get the 2 of them equal to each other, and then you can just set them end to end. So if you don't like plugging one, like it's another option. It may not be shorter, but sometimes it involves less multiplication at least. And it appeals to the way that my brain visualizes information. So, I left the 8 out, sorry. Now we've eliminated T as a factor, we can just solve for A. Since A is negative on the left, I'm going to send all the A's to the right and all the not A's to the left, just to try to get rid of the negative sign. That's going to look like 50 minus 32 equals 10.2a plus 5.1a. This is why we needed to make it negative in the first place, so that it would eventually end up being positive over here. And if we didn't do that, the final number would turn out very differently. Any questions, issues, etc. arriving at this point? All right. All these don't have unknowns, and all these have the same unknown, so bless you. The addition and subtraction can proceed as normal. 18 equals 15.3a, and lastly, A equals 18 over 15.3. Therefore, A equals, correct me if I'm wrong, approximately 1.18 meters per second squared. So that is the acceleration of the entire system. Directions will change based on object, but that is the magnitude of acceleration of the entire system, regardless of direction. How do you guys feel? All right, no objections it seems. And again, that is just the answer to magnitude. If I specifically asked about one object's magnitude and direction, then for each single object you want to specify axis and positive and negative and things like that. But if it's just magnitude of the whole system, we've already answered the question. And I know in this class that sometimes the numbers just feel like numbers. They may not have any bearing in reality. So I like to sometimes take a second and explain why a number makes sense in the context of reality. So let's examine this answer very briefly. Acceleration is 1.18 meters per second squared. The two objects share the same magnitude, so that's the rate at which box 1 accelerates forward. And it's also the rate that box 2 accelerates downward. And that is specifically an acceleration downward. It's going to get faster and faster the longer that you allow this to happen until it hits the floor, right? Which is similar, but distinct from falling. Falling is also getting faster and faster downward until you hit the floor, right? The main difference between this and falling, though, is falling is an acceleration of negative 9.8, whereas this is much slower. Still down from box 2's perspective, but it's slower. And that makes sense, right? Box 2 is being held up by this rope. The rope's not enough to fully support it, but it's enough to slow it down, right? It's kind of acting a little bit like a parachute or a really bad bungee cord. It is preventing box 2 from descending at the full rate of gravity. It's at like 1/9 the rate. So the rope isn't stopping it, but it is slowing the process down. So the number there makes sense. If we got a bigger number than 9.8, then that would be a problem. But we did. This makes sense. We go home happy. Does that feel all right as a sense of scale? Sense of interpretation? Okay. One sec. Stay hydrated. Now, as per the usual rules of two equations, two unknowns, once you find one of the unknowns, you can just pop it back into any of your previous formulas to find the second. So I'm going to take that 1.18 and I'm going to pop it into box 1's x-axis equation because there's fewer negatives to deal with that way. Tension will equal 10.2 times 1.18 plus 32. And if memory serves, please let me know if I'm wrong. That should be about 44 newtons. Excuse me. Any issues or arguments arriving at that number? And you could use the other equation to do the same thing. You get the same result. And kind of like what I did a second ago, examining whether that number makes any sense, I want to do the same thing here. This is the tension that the rope is going to use to pull on both objects in different directions. In box 1's perspective, that means it's going to be pulled forwards by 44 newtons and backwards by a friction of 32 newtons. That means the tension is stronger than the force of kinetic friction, and that's why it's going to move forward. So this answer makes physical sense. If this number was smaller than 32, we'd have a problem. But it's bigger, it's going to move forward, so that makes sense. Now, meanwhile, from box 2's perspective, 44 is gonna pull up where its own weight of 50 pulls down. So the net force there would be -8 downwards. And so the same tension creates a different result on the other object. Even though it's the same tension, box 2 is gonna descend down. So for box 2's case, tension is not enough to overpower gravity, and that's why it proceeds down anyway. And again, that makes physical sense. We know it's gonna move down, right? So for box 1, we expect T to be bigger than 32. And from box 2, we expect T to be smaller than 50. And that's exactly what we got. So I'm satisfied. How do you guys feel? Everything make physical sense? Or as much as it can? All right. And with that, we're done for the day. And this was a big, weird, long example, so if things are still settling in your brain, if things still don't make complete sense, that is fine. This is, again, like the culmination of the past week plus. So if this needs time to settle, that's fine. I'll also point out that when I write tests and homework assignments, there's usually like one big one. This would be like the most amount of math I'd ever expect you to do by yourself. This would be like the big question on the test. The one that I give a lot of partial credit for. So if
The
you
test
think
is on
this-
the 6th, correct?
The test is the week of the 6th through the 11th.
Oh, so it's not our lab day.
Yeah. So, thank you for reminding me. I'm gonna pull the calendar back up. I wanna keep saying it so that everyone, sorry, someone in the hall was asking something and my brain just assumes question tone, I must answer. This is today is September 20th. My goal for the next 3 lectures is to do chapter 5, and that gives us at least one full lecture before, oh, it's the week of the 2nd through the 6th, sorry. First week of October is the week of the test. So the way that that works again is lecture will be review time. We're gonna go over like study guides and things like that together. And you guys can ask questions from the study guide and from homework and stuff. And then during your lab time, you will come and take a 1-hour test in a 3-hour time slot. So you just show up whatever day of the week you have lab, and you can switch sections if that benefits you. Some people do it on Monday to get it over with, some people do it on Friday to get more study time.
And since you're doing just review during lecture that whole week, you're not covering new material?
Not really, no. Yeah. Now, if you still show up this week, I recommend you either bring study questions or you bring questions to distract me. Like if you watched, Superman recently, ask me how he flies. Because I can talk about that for 50 minutes. So yeah, lecture this week will be review. If you take the test Monday, showing up will be review for a test you've already done. So either come because you want to or come because you have silly science questions. Yes?
Sorry, I already forgot. Is the week of the 2nd or the 9th?
The 2nd.
Okay.
That is because fall break is the 9th and the 10th.
Oh, okay.
So no lecture that day, no lab that week. In fact, we would meet Wednesday and Friday for me to give you the test back and to talk about your midterm scores. Does that answer any questions for now?
Midterm scores basically consist of that test.
Yeah, so midterms go out on Friday the 13th, ominous. And for this class, your midterm score is your current class average. So test plus all the homework up to chapter 5, plus all the quizzes up to chapter 5, plus all the labs we've done.
Oh shoot, forgot about labs.
Yeah, labs is part of the course. This is one 4-hour class, not a separate 3-in-1.
Are our labs graded right now?
Yes. Now, as long as you show up and do them and accept feedback and fix everything before you leave, each assignment is 100, and the course is waiting for that. Each lab assignment is 100.
Because I haven't been told if we've gotten